Welcome to our tutorial for question 15 of our weekly review. Question 15 is asking us to identify transformations of shapes on the coordinate plane, as well as to describe the specifics of how those transformations are taking place. For us to be able to identify these different transformations, we first need to know what the transformations are. There will be 4 different transformations that we learn about this year, although there are more transformations than this. These 4 different transformations can fit into 2 categories. The first category is called a rigid transformation. And a rigid transformation, the location of the shape will change on the coordinate plane, but the shape itself will remain exactly the same. This means that if I start with a 2x2 square, that I'm going to end with a 2x2 square. It's simply going to be in a different location. Our second type or category of transformation is going to be a non-rigid transformation. And in a non-rigid transformation, the shape itself is going to grow or shrink. And when it grows or shrinks, its location may or may not change on the coordinate plane, and we'll talk about that a little bit more as we go forward. Our shape is going to grow or shrink, so again, if I have a 2x2 square, that means I might end up with a 4x4 square or a 1x1 square. Now, for rigid transformations, there are 3 types of transformations. They are called reflections, rotations, and translations. And there are some words that help me remember the differences between these. A reflection is simply the shape is going to flip on the coordinate plane. A rotation, we can think about like the shape spinning on the coordinate plane. And a translation, we can think about the shape sliding on the coordinate plane or moving on the coordinate plane. Remember, in all 3 of those examples, the shape itself remains the same. It's just its position that has moved. For our non-rigid transformations, we're going to have what's called a dilation. And a dilation is going to be the increase or decrease of the size of the shape using a common scale factor. Now, one of the things that's really important here is that the shape itself is changing its size, but it will never change the shape. So if I start with a 2x2 square and I end up with a 4x2 rectangle, that is not a dilation. Something else has happened in that situation. If I start with a 2x2 square, I should end up with a 4x4 square or a 6x6 square. That would be an example of a dilation. It should still be a square. So we're going to keep those 3 different descriptions up here to help us. And let's go ahead and take a look at some examples of our different types of transformations. The first 3 transformations that we have here are rigid transformations. And you can look at all of those triangles that are there, and you're going to notice that the first triangle looks exactly like the second triangle, but the location itself has changed on the coordinate plane. We'll start with the translation. The translation, you're going to notice that the orientation of that shape is still the same, meaning that the corners are still in the same position of that shape. It's still obviously the same type of triangle, but it has simply slid on the coordinate plane, and it looks like it's kind of slid up and over a little bit. Our reflection, we can see that the orientation of that shape has shifted. You can kind of think about this like a mirror, and that red line that's there in the middle is what the mirror is, and the reflection is the resulting image from that. Our orientation on our reflection has flipped in this case, and that's our key word to help us remember these types of transformations. Finally, we have our rotation, and you can see that the triangle has rotated or spun around a specific point on the coordinate plane, and all of those points have spun the same amount or the same degrees. They've changed by the same degrees on that coordinate plane. We also have our dilations. Again, you're going to see that the shape is the same type of shape. It started out as an equilateral triangle, and it's going to finish as an equilateral triangle. It hasn't turned into a rectangle or a square, and it hasn't even turned into a different type of triangle like a right triangle or an isosceles triangle. It's going to stay the same type. But what we are going to notice is that it has increased its size. All of the sides of that shape have increased their sides by the same amount. That's what's called our scale factor. Let's go ahead and look at this in practice. These first three transformations that we have are definitely rigid transformations. And I can know that right away because all four of these shapes look like the exact same shape, but it looks like their positions have moved on the coordinate plane. In this case, we're going to start with shape T, and I'm going to outline that there in red so it's nice and easy for us to see. We're going to go from shape T, and we're going to look at shape T primed. T primed is going to have a little 1 in the top corner of that. So you can see T primed outlined here in green. Now, as I'm trying to decide what type of transformation this is, I know it's a rigid transformation, so I can narrow it down to the 3 rigid transformations that we know about. In this case, I'm going to notice that T primed has spun on the coordinate plane. So I would describe this as a rotation, or I could say that this shape rotated, and I want to describe how that shape rotated. In this case, it rotated 90 degrees clockwise. I also want to make sure that I'm using coordinate points on my coordinate plane to describe this. And so I'm going to identify the point of rotation. In this case, my point of rotation is going to be point 2, 5. That is the point at which this shape spun around. In this example, that point is on the shape. And just realize that sometimes, like we saw on our last page, that point of rotation can be a point that's not on the shape itself. Next, let's go ahead and look at T double primed. I'm going to outline this one in purple so it's nice and easy to see. I'm going to notice that the orientation of this shape has shifted, and this is a pretty good clue that I am working with a reflection. I also want to make sure that I describe how this shape has reflected using the coordinate plane, and so this has reflected across the y-axis. If I draw a purple line of reflection there, I'm going to notice that that is the point of reflection or how things are being reflected. Now, if I'm not sure of that, what I can do is I can count how far the corners or the points of my shape are from that line of reflection. And they should be exactly the same distance away from T2 primed to the original T shape. So here I'm going to count and notice that B2 primed is 1 space away from that line of reflection, and so is shape B, or point B. And I can do that with A2 primed, which is also 1, and I can also do that with C2 primed, which that time it is 2. And that's how I can find what that point of reflection is, or that line of reflection is. My final example is going to be shape T triple primed. In this case, I'm going to look for my T with 3 1s in the corner. And I'm going to notice that that orange triangle and the red triangle, the orientation is exactly the same. That's a really good clue that this has been translated. So I'm just going to describe this as being translated. Now, as I do that, I want to also make sure that I'm describing specifically how it translates. So I'm going to notice that the x coordinate points all moved to the right by 4 spaces, and the y coordinate points all moved down 4 coordinate spaces. So I'm going to describe this as x plus 4 and y minus 4. Now, I could test this with all 3 of the points, But for example's sake, I'm just going to use one point, point B. And I'm going to notice point B moved over to the right 4 spaces and down 4 spaces. And that's where we get that description, x plus 4 and y minus 4. Let's go ahead and look at a dilation. Here is a triangle. And again, we're going to notice that the smaller triangle and the larger triangle, they look like the same type of triangle. It hasn't turned into a right triangle or something like that. The proportions of the shape should still be the same. I've counted the bottom side, which is 3 across. Line AB is 3 across. And I can also count the bottom side of my bigger shape, which is 9 across. That can tell me that my scale factor is a scale factor of 3. In this case, I know that because 3 times 3 is equal to 9. So my scale factor is how did I get from my original shape, line AB, which was 3, to my new shape, A prime, B primed, which was 9, and I'm going to simply multiply that by 3. Now, if I try to measure those other sides, this is going to become a little bit difficult because I'm working with diagonal lines, and so that's pretty tricky to measure out. But once we know the scale factor, we can actually use that and the 3 points of our triangle, or if we're working with a different shape, we can use the corners or the vertexes of that shape. In this case, I can simply multiply the coordinate points for each point A, B, and C by my scale factor, and that will tell me exactly where my new shape is going to be. So I'm going to notice point A is located at 2, 1, and I'm going to multiply both of those coordinate points by 3, and that's going to get me to 6, 3, and I can look at my big shape and notice that A primed is located at 6, 3, so I know I'm correct. I could do the same thing for points C, which was located at 3, 6. I'm going to multiply both of those points by 3. I'll get 9, 18. And again, I'm going to notice that's exactly where point C primed is located on the coordinate plane. Finally, I'm going to do the same thing for point B, which was at 5, 1. I'm going to multiply each of those by 3, which will get me to 15, 3. My new location of this. And this is an example where we do a dilation where the shape has actually moved as well. Okay, so sometimes that shape might stay at least partially in the same spot, and sometimes it might move. And this is an example of where that shape might move when we do that. That should give you a good understanding of our 4 different transformations and how to work with them. If you need a little bit of help with other figures and whether those figures are similar or not, we're going to talk about that in question 16.